Hello and welcome back. So let's continue on solving some LeetCode hards today as well. Let me choose some problems. I'll probably start with some problems with having those have higher acceptance rate, and then we'll move on to the harder ones. Let's try this. This is locked. What else? Sum of perfect square ancestors. Maybe we can try this. Yeah. Cool. Maximum subgraph score in a tree. You are given an undirected tree with n nodes numbered 0 to n. It is represented by 2D integer array edges of length n minus 1. Okay, you are also given an integer array good of length n, where good of I is 1 if the ith node is good, else it is 0. Score of the subgraph is the number of good nodes minus the number of bad nodes in that subgraph. For each node I, find the maximum possible score among all connected subgraph contain that node. Subgraph. A connected subgraph is a subgraph in which every pair of its vertices is reachable from one another using only its edges. For each node, I find the maximum possible score among all connected subgraph containing that node. Okay. So ideally, answer for all the nodes in that subgraph should be same. So 0, answer for 0 and 2 is same, which is 2, and 1, 3, 4 is same, which is 3. And that is one of the observations. One more thing that we can think of is they are asking us to find out the number of good nodes minus the number of bad nodes. So what we can do is simply assign good nodes as +1 and bad nodes as -1, and find the sum of values assigned to them. We need to maximize that. How we can do that? If the tree was rooted, I can think of a solution where we find out the maximum achievable answer for any tree rooted at a particular index. For example, let's say we wanted to find the answer for node 1, then we just need to find out the maximum sum of subgraphs. So let's say we start at 1. The answer for 1 without considering any other limits is either +1 or -1 depending on what is the score assigned to it, and we choose whether we want to find out the answer, merge the answers from either of its children's. That is how we can find out the answer for a particular node, but we can do this for all the other nodes. With this approach, I can find out the answer for all the nodes starting with its subtree. And I think we can do some rerouting logic here. So for the answer for node 3, it already includes answer for node 4, but if we want to include 1 in its calculation, then I need to exclude 3 from it and take all the other candidates. Correct. So let me draw something. So we had like 1, 0, 2, 3, 4. Let's say the answer for 3 is already computed because this is a subtree starting at 3, and answer for 1 includes the entire tree. I need to exclude it so that I add this orange part in the answer. So answer for 3 should be incremented by the orange part, which is answer for 1 minus answer for 3. These don't necessarily mean the equations for computing the answers, but what I meant by this is, let's say, we start at 1, we compute the answer for all the subtrees. Then for finding out the answer for any intermediate node, let's say node 3, we need to take this part as well. And answer for that part, let's say orange part answer, will be calculated by taking so for rerouting, what we usually do is we bring down the parent node below it so that this becomes the root, and if this is the root, we already have computed the answer for this. Just need to remove the contribution of answer to this from the parent node. I think I forgot how we implemented this, but let's try. We are given 3. The answer could also be negative. I mean, whether to choose this subtree, whether this subtree was included in the answer for node 1 will be only if the answer for this is greater than 0. Because if it is less than 0, the answer for node 1 would anyways be reduced, and which is not the right approach. So if that is the case, I can start with so if we were traversing the tree like this, this was the parent, this was the child. Before moving on to this node, I need to remove the contribution to answer for child node in parent. So I just check if answer for child is greater than 0, then answer for parent should be decremented by answer for child. After this is done, we move on to this node as the root node of the DFS traversal. Then answer for 3 would be like sum of maximum taken over 0, answer for all of its children. C belongs to adjacency list of child. I can try that. I'm not quite sure if it will work. Maybe I can move and try another problem. You're given an integer n and undirected tree rooted at node 0 with n nodes numbered from 0 to n-1. This is represented by a 2D array of edges. Length n-1, where edges of I is ui vi. You're also given nums where num is the positive integer assigned to the node I. T of I is the number of ancestors of node I such that the product number of ancestors T of I is number of ancestors of node I such that the product is a perfect square. For all the ancestors, the product of the value assigned to node I times the number of value assigned to its ancestor is perfect square. What are the constraints? It is quite large. Define value T of I as the number of ancestors of node I such that the product is a perfect square. Okay. Let me formalize this. So let's say I have a node. Let me use a better color for this. So let's say this is node I. And there are multiple ancestors for this. So this was root node. Let's say the ancestors for X, Y, and Z. And let's say this was, let's not call this root. Let's say this is root. Sum of T over all T. Okay. So for each node I need to find T of I, which is like 1. Means sum of all the values. It is 1 if the value assigned to node I multiplied by value assigned to this one of its ancestor is a perfect square. Let's say x square, not x, but this is like some constant square. It's a t, and the nodes are quite large, so we have about 10⁵ nodes. So for each node I need to find out product of all of its ancestors, which can take order n time. So total it could take order n square times. How we can optimize this? Let's think of some approach. Cool. Let's say this was node U. Node U is an ancestor of all the elements in its subtree, all the nodes in its subtree. So if we take this particular subtree, then node U should be taken as a product with everything, but we want to find out individually. So this node U will should have been taken product with all of its node in its subtree. Are the values smaller? No, the elements are also about 10 raised to 5. So the product is about 10 raised to 10. Define a value t of I as the number of ancestors of node I such that the product of their values is a perfect square. Okay. Product of values is a perfect square. I was thinking whether we can do this in a top-down manner, because if we want to go from bottom up, so we are at node U, then we have to find out all possible products, which is not something we should ideally do. But let's say we are at node U and we are doing a depth first search traversal. We can store information about all this parents somewhere. So for example, let's go with, why are we given edge if it's a tree? Undirected tree rooted at node n, node 0. So if we have at any node U values of its parents, ancestors of U, let's say this is stored somewhere, and value at node U is num of U. We want, let's call it this X, and one of these values taken as Y. So we want X into Y as perfect square, which is some constant square. So these can range between 1 to 10 raised to 10, because these are about 10 raised to 5. And the way we find out whether a number is a perfect square is by finding out its prime factorization. So let's say X into Y is p1 raised to alpha 1, p2 raised to alpha 2, pk raised to alpha k. It's a perfect square when all of the alpha i's have modulo 2 equals to 0. So these exponents should be even. That is the condition for perfect square. In this equation, we know what x is, only what x is, nothing apart from that. Let me rewrite this. X into y is even alpha 1 to alpha 2 and pk alpha k. We know this. This is known. how we can use this fact. So perfect square. And these values are also stored somewhere. So let's say we can do a fast lookup on this, but still we have like order n values in this set, which is the ancestor for any node u. How we can use this fact. One thing that is visible from the constraint is x belongs to like 10 raised to 5 maximum value. So the number of prime numbers, like the cardinality of prime numbers for below any number n is like square root of n. So k is less than equals to square root of x, I think. Number of unique prime numbers in this. But since we are dealing with product, I don't think and one more constant is alpha I is less than equals to, so maximum product maximum exponent could be like 2 raised to something, let's say 2 raised to I, which is less than equals to 10 raised to 10. So let's call it like 32 or something, or for worst case let's say it is like 40. And this product alpha I pk this still doesn't help in any way. Let me think of some approach, something else. Number of ancestors of node I such that that product is a perfect square. Product is a perfect square. There has to be some fact related to this constraint 10 raised to 5. X into y. Okay, there are two unknowns in this equation, so I'm still not quite sure how we can leverage this. But one thing is for sure, that alpha I is either, I mean, it's not 0 or 1, but we can say that this belongs to 0 to 40, and alpha I mod 2 is 0. So if we had to shift this x on the other side, then y would be p1 alpha 1 minus some constant, let's say c1, which is the prime factorization of x. So let's say prime factorization of x is p1 raised to c1 raised to c2 all the way up to pk ck. This p2 alpha 2 minus c2 and pk alpha k minus ck. Here alpha I should be greater than equals to c of I. And since this is a, I mean, this was a perfect square, so alpha I, my alpha I mod 2 was 0. So if I had to subtract C1 from it, alpha I minus Ci should have the same mod 2. Am I writing this equation correct? Alpha I mod 2 is 0. So we just need to check the parity of C of I. So let's say C of I is mod 2 is 0 or 1. If it is 0, then alpha I is even. We want alpha I to be even. And if it is 1, then we want alpha I to be odd. This is based on what is the coefficient or exponent of I in x. Once we have this equation, we have like y is p1 raised to even or odd. So let's call it parity, or let's say, so we only have even or odd condition, right, for the exponents. This is like even odd, even odd, all the way up to even odd. Once we have this, let's say take some example for this case. We want p1 raised to, but we still don't know what p1, p2 and p3 all the prime numbers are. So this is like, let's say, odd, even, and something like that. This is what we arrive at. What we can do after this is, let's start. Y will also have some, like all the elements in Y, which are the ancestors of node U, will have some values. It is possible that it has more prime numbers than the elements in this sequence. What else? Let's think of something else. Maybe I can spend 5 minutes on this and move on if it is too hard. I was at this point. How do we usually check whether, I mean, the problem is as simple as saying how many, you are given an array and you want to find out how many pairs of elements have product as perfect square. The problem is as simple as that. And the constraints are like, this is up to 10 raised to 5. We don't know what that perfect square is. There are two unknowns in this equation. Think what else can be the trick here. So if this was a perfect square, then the prime factorization will have values like 2 raised to alpha I and minus whatever we have the exponent for this. Let's call it EI. This should have mod 2 equals to 0. No. This is something what we get after we move x to the other side. Ideally, 2 alpha I minus EI, this should obviously be greater than equals to 0. And what else? So if this value, we just need to check the parity for this. Let me see. So if E of I is mod 2 is 0, then we want 2 alpha I minus 0, which is like it's always even. So y's prime factorization for prime number E of I, the exponent should be even. And if E of I mod 2 is 1, then it would be 2 of alpha I minus 1. So ideally, this is an odd number. So we want the other number to be odd. Correct. And we don't care what those prime numbers are. And ideally, they should be the same as what we have in x. So x into y is that sequence that we saw earlier. And after this is transformed, we get something like e1 raised to even odd. We only care about the parity for this. And these numbers could be something else. Let's take an example. Let's say x was 2 raised to 3, 3 raised to 5, 5 raised to 4, 7 raised to 1, 11 raised to 3. So in this case, y could be, it must have 2 raised to odd power. It must also have 3 raised to odd power. It must have 5 raised to even power, 7 raised to odd power, 11 raised to odd power. Apart from that, it can also have any other prime numbers which must have even exponents. So it could have something like this. We only care about what these exponents are, and we need to find out how many such y's we have. So I think we can just transform this into two raised to odd, 3 raised to odd, 5 raised to even, 7 raised to odd, 7 raised to odd. We have a sequence something like that, which is something like this. let's call it mod, and like 0 or 0 and 1 makes some confusion. So this is 1 1 0 1 1 2 3 5 7 11 is the sequence of prime numbers as they occur. So this, and so if I had to transform every number in the nums array given into something like this, which is a vector of zeros and ones, where let's say this is t of I. T of I is 0 if alpha I, which is the exponent of ith prime number in nums of I, is even. It is 1 if alpha I is odd. So once we have all of these vectors, and the maximum length of this vector could be, I think, square root of 10 raised to 5 unique prime numbers below 10 raised to, number of unique prime numbers below 10 raised to 5. Once we have this, I just need to I can check. So we have like sequence like 1 1 0 1 1. So what are the valid values of y for this combination? It could be, and it must have these values. Does it need to have anything else, or is this the only format that we expect it to be? So even if it has multiple other prime numbers like we saw here, their coefficients would be 0, and they would be taken care in this sequence itself. I mean, the problem literally boiled down to saying you prime factorize x, you create a binary number 0 1 0 1, which has this definition that we saw earlier, and just check how many of the ancestors have this representation. I think that's true, because let's say y was something like this. It has this sequence, but somewhere else it has 1. Then that is not allowed, because we don't want any other prime number to be having an odd coefficient. So this is false. So there won't be any other ones apart from this at these exact locations. I think the proof makes sense. So my algorithm would be, first of all, for each nums of I would prime factorize it. And for prime factorization, I will create a, like it, this has like, how much is 10 raised to I think this is like something close to 300. This is a vector of size 300, and each element is like 0 1, and I can store a map of this vector to count of these. So I just need to maintain the frequency of these vectors. I can also use a bit set here, but let's first start with the easiest way to implement it, and I'll check if it times out. I can try to optimize it further. Let's move on to the implementation. One more thing that I wanted to do is, I don't want to use this ID I'll just let me remove this Vim key binding. It doesn't copy. In that, so we have 3715 as the problem. 3715. Solution. Let me zoom out a little bit and move my camera to the right hand side. Cool. Let's implement this now. We'll have to refer the problem. Okay, so we have n and all the edges are given and the array is given. Okay, so let me first of all get this. This n is n. We have edges and the values. Let's call it a. This of a is nums, and let me also create a vector of integers for the adjacency list. dj dot resize n, go over all the elements. Let's say this is e in edges. Adjacency list of, we have only 2 elements in the edges listed. Okay, e of 0 dot push back e of 1. And since these are not parents, I need to do this in a undirected fashion. Once this is done, I can start the TFS. I also need the prime factorization, so let me think how I need to implement this. First of all, I've created the adjacency list. Are these 0 based or 1 based? Values for all nodes belong in this range. Okay, so this is fine. Okay, this is 0 based. What I wanted to create is a vector of integers. Let's call it prime factorization with parity, and this is for every node. So it will have size n, but what's inside it will differ. So I'm assuming that n square root of n solution would be sufficient to solve this. I'm just moving with that hope. Let's say this is pf parity, and for each of the elements in nums, pf parity of I is a vector of some size. So let me write a utility function for this. What I can do is I can start with, or should I use some template? Let me use my template instead of writing this from scratch. Pf parity of I is prime factorization. Prime factorization. I don't have prime factorization. Let's use this. Maybe it's in SPF. SPF. Okay, let's use this. So we want prime factorization until this. Let's use max. This is 10 raised to 5 plus 1. So we have calculated prime factorization. Sorry, we calculated the smallest prime factor for every number from 1 to 10 raised to 5. And to get the, what did we name this function? Okay, why is this broken? Okay, vector of int get prime factorization for any number, let's say x. Do we have elements with value 1 in this? Yes, we do have. They should also be included in the answer if they should be included if x is already a perfect square. So like prime factorization for 1 is like 2 raised to 0, 3 raised to 0, and so on. So that would be sufficient, I think. One thing that I wanted to do is find out what should be the size of this individual elements in this pf parity of I is some vector. Let's do it here. So number is prime if its prime factorization is same as its smallest prime factor is same as the number itself. What I can do is let's initialize a variable count. This count is incremented every time we find a new prime number. I think that is also not required. What I can do is I can simply find out all the prime numbers. Vector of int primes. Let's store them. Primes dot push back I. So I is prime. And while constructing this list of zeros and ones, I just need to go over all the primes. So this is vector of int list, return the list, and as long we just need to find the coefficient, right? So let's say this is alpha. Alpha is 0, while x mod p 0, we need to divide it and increase the alpha. And once we find that, I need to insert it in the list. Let's keep the SPF part. We don't need it. Okay, once this is done, we get this list. So this is like get pf how can I run this function once for all the test cases? We want that actually. C++ run function once globally. Okay, is there any other way? Okay, this is the function that we want to run, and we create a struct and initialize it in the constructor. Let's do that here. Run once, and we want to run the SPF function. So this will still not run because we want to create one instance of it. I think we can create instance like this. What's the error? Let's do it as suggested here. Okay. This will run the SPF function to initialize all the prime numbers once for all the test cases if the test cases are being run one after the other inside of one single main function. So this should be nums of I. Once we have this, I need to call DFS. The root node is 0, I think. Yeah, what is the, yeah, rooted at node 0. So let's call DFS at node 0. And we also need to have parent to track, to not go into a cyclic loop while performing DFS. This is node U, parent, or int v, which is child of u. So it should be in adjacency list of u, but a parent will also be in the adjacency list of u because we have created the edges in unidirectional form. So if v is not equals to parent, we need to perform the DFS on v, and parent is u for node v. And since we only care about the sum of answers, let's store it in a single variable answer. And what else? Before moving on to the next node, I need to update. So let's the map that we talked earlier. This should have vector of int and int as the counter. This is frequency. I need to increase the frequency for PF parity of u and decrease it after it's computed. And here I just need to add the contribution in the answer. PF parity of, not PF parity, it should be frequency of PF parity. It is not u, or is it? So I'm passing nums of I here. So this is the exact value at that node, and I'm assigning it to the index itself. So yeah, I think this is correct. Cool. Let's try running this. I need to return the answer from here. Let's try this. Let me check if this compiles locally first. G++ .cpp. We got the answer incorrect. Output is always 0, or okay, we got one answer. 3 nodes, values are like this: 282, 0, 1, 1, 2. So this is like a chain. Let me go to the sketchpad. So we had like 0, 1, and 2. What were the values written to them? 282. So this would have produced a vector like 2 raised to 0, so it should be 0 0 0, something like that. This should also be 0 0 something, and this should also be 0. So ideally this should have been clubbed with this, so this contributes 1 to the answer. This should have been clubbed with this and this, contributing 2 to the answer, and the final answer should be 3. But my answer is 1. Let me debug it further. No return statement in function returning non-void. What does that mean? 77. Did I not save this? Let's use standard C++ 17. We even don't need this vector A. What else? E0, E1. Let's make this long. Let's also debug this once. What else? I mean, this could be very large ideally. Let me check if this function is correct. Let me use something else for now. Prime of max plus 1. Write this again. So ideally we do it like this: prime plus max plus 1 as true, and we go over all the elements. I equals to 2, I is less than equals to max. We check if it is prime. If prime of I, let's add it in the primes list, and we mark all of its multiples, say starting from 2i all the way up to the max limit. Multiple starts at 2i and adds I to itself, and we need to mark it as non-prime. Let's try compiling this. We'll try this once. Yeah, I also need to print the vector. And let's only print like top 10 elements, because we only have smaller values for the example test cases. Nums of I. For int I0, I is less J0, J is less than 10, and J is less than EF parity of I dot size. J++ C out. Excuse me. Check this. Why do we have 2 raised to 1 here? Okay, got it. I need to have, oh, let's make this fancy XOR. Cool, let's try submitting this. I think that should timeout. I forgot to remove the log lines. Okay. Let's use this test case itself. And I want to remove this. What else? Maybe I can make this a little faster by using an ordered map. Solution is implicitly deleted because field frequency has deleted default constructor. What did I delete? Let's try this first. Okay, it does pass, but I'm not sure if it is fast enough. $661 of 695 test cases pass, so ideally this should pass. Let's see. Otherwise, I'll have to think of some other approach. So right now the time complexity is not that high. What I can do here is make this a little faster by only going through or instead of a vector, I mean this should be a vector of boolean. Why am I using a vector of integers here? Or should I just go ahead with something else? Maybe we can start with, and we can use strings as well here. But I am not sure if this is the bottleneck. So this overall thing is like n square root of n time. If that itself is slow, then we can't do much. Let's try. Let's try with some optimization. Then let's see if there are some improvements because we are at 668. So for this, first let's try with the Boolean approach. Return a list of Boolean. This is a vector of Boolean. PF parity should also be a vector of Boolean. Okay. Let's try this. After this, I will try the storing the values as string approach. Don't need you. So we were at 668 with the previous approach. Let's see if we can improve. Okay, it is worse. Let me go ahead with strings. String list. So if alpha is true, then I need to add 1, else I need to add 0. There should be a string, and this also should be a string. Are we good? Okay, let's try this. The string itself is quite long. Okay, we got slight improvement. We were at 668. We went to 678. Let me also try this unordered map thing. If this doesn't work, then I'll probably have to think of something else. 678. The next thing that I would like to do is convert these strings into zeros and ones. So once we have all of this, we are storing these strings. We just need to find out the count of unique of them, right? So it doesn't make sense to store the entire thing and use them as a prefix to this map, because these lookups would be very slow. So I'm trying to replace this map with, what do we say, a list of integers or an array. So let's do that. So let me create a set of string unique values. So I think this is sort of coordinate compression. So every time we find a unique value, we create an ID associated with it. Let's say ID is 0. And let's make this parity of I should be integer. This should be integer now. So we had get pf of nums of I. This will return us a string. On string value is this. How do we check that? What is the ID associated with any unique thing? Do I also need a map? Pf parity. Set of string. I'm trying to avoid a map here. But it could get lengthy if that is not the case. Let me think what I can do else. If this particular value is present in this, then I just need to assign f parity of I as unique of value. Otherwise, I need to increment the ID. Parity of unique of value is ID plus plus. I think this should be correct. So for the frequency part, we just need a vector of integers frequency, which should be initialized with size. Let's say n plus 5, just to be on the safer side, because we will have at most n unique values of these strings. And yeah, do we have any other errors? No. Okay, let's try this. Cool. So we were at 678. Let's see if there are any improvements now. Okay, hardly one test case has passed. So I'm not quite sure if this is the correct approach. The bottleneck is still this part. So we are still using a map. What if we use unordered for this? Reference binding to null pointer of type int. What? Still the same. My solution is correct, but let me think how I can probably make this faster. These test cases have quite large numbers. Let's see what part I can make faster. So we start with I all the way up to. This is being run once for every test if the tests are being run individually. This is like 10 raised to 5 and n log n. This is fine. 2i. Okay. What else? So this is fine. String list. We're going over all the primes. And should we skip when x is like 1? Let's say while x is greater than 1 and this is the condition. Because we are by default adding multiple zeros at the end of this sequence. But do we actually need it? So let's say the sequence was something like this. Starting from p equals to 2, 1 0 1 0, something like that. And the other one was like this. So this anyways would never match. So ideally we should stop here itself. There is no need to add zeros and keep them like trailing zeros, a lot of trailing zeros at the end. Let's try and verify this. Time error. X is greater than 1 and this condition, so this should be fine. Is there an issue in my local code? We are hardly making progress of one test case. I want to solve this problem once. I've been sitting for like 2 hours and haven't even solved one problem. Okay, that's fine. This looks like a linear tree. No. Let's frame the problem a little differently. So what I did is created this string of zeros and ones, right? Maybe we can think of something else. We want the exact prime numbers. We just need like this sequence of zeros and ones. The sequence of zeros and ones is like saying you want 2, 3, 5, and 17, for example, as odd exponents. And if you look at this list, this by default has a maximum size of 40. We saw right, 2 raised to 40, max goes all the way up to 10 raised to 10. So instead of storing the zeros and ones, what if we just store what all prime numbers need to be having odd exponent? Let me try that. So let's make it list only. Vector of integers. Vector of integers. If alpha is odd, this list must have that prime number. Okay. Now once we have this, let's forget about this. What was that? If parity. If parity of I is this, what is the error here? So like this should be again vector of integers again, and we want this map to be a vector of integers. Let's remove this. We don't need this. Cool. Let's try this now. Okay, let's submit. We are at 680. See if this make any difference. We are at 692. Wow. So we are like at the last end. Like hardly 2 or 3 test cases are remaining. Total optimization that I can do. Let's also use this test case just as a reference. This does pass in like 1.8 seconds, but yeah, whatever. I can probably convert this into BFS if the part of stack unwinding is slow. But let me find out the major contributor. This P of parity of I, I'm finding out all of them. Instead of that, what if I just, it's possible that all of these numbers are unique, but that is also not necessarily true. Let's do one thing. Let's cache this function. Instead of that, I can also create this globally once for all test cases. Not all test cases, but yeah, I can also do that. So what I wanted to do is PF parity. Let's move this outside. Let's make this PF parity max plus 1. No, this is assigned to a particular integer node number. So we can't do this outside. This is node ith value for node I, but I also don't need to store that. So let's do this vector of integer. Let's say odd primes. Odd primes in the prime factorization of every number from 1 to max, and inside it here I'll call that, so for int I equals to 0 or 1 is 1 I less than equals to max I plus plus. Why is this broken? Okay, we want odd primes of I equal to get PF for I. Let's move this upwards. Delete this. Once we have this, we don't need to store PF parity. It would be something like odd primes of nums of u. I need this vector outside. Okay, and one more thing, I need to remove this, and this of nums is nums. I don't need to do this thing. This should be fine. Let's try. Okay, so we were at 692. Let's see if this passes. We've spent quite a lot of time on this. Perfect. I mean, the time reduced too drastically. We were at like 1.8 seconds and this ran in 478 milliseconds. So I think this was the expected answer, I suppose. a lot of pre-computations, but yeah, I just want to move ahead to the next problem. Then we'll probably solve some mediums now and then stop the stream. Difficulty medium. Okay, let's open any random ones. Number of centered subarrays, smallest all ones, multiples, complete prime number. Cool. I actually want a better setup to run this LeetCode problems locally. Maybe I can do it in some live stream. You're given an integer nums, a number num is a complete prime number if every prefix and every suffix of num is prime. Okay. Yeah, I mean just case by case. Let's convert this to string first. Every prefix and suffix they are asking, right? So yeah, cool. So n star is toString of n. We want this size, let's say length as, I'll probably write this in my local terminal. Which problem is this? 3765. Okay, CD 3765 E. So length is star dot size. Go over all the prefixes. I is less than length I plus plus. Let's construct the number prefix. Let's do this twice so that we don't repeat the code. Is less than 2 red plus plus. Let's say this is num, and we are constructing num by taking each character from the prefix, and it after the first repetition is complete I need to reverse the string. Reverse. Do we have a reverse method on string? Yes. No, I don't think so. Reverse star dot begin and star 10. Cool. So I need to add this character in num, and this should check all good. Let's say all primes. Primes is true. I think I can check every prefix and suffix using the square root approach for finding whether a number is prime or not, instead of just doing any pre-computation. Let's do that. All primes should be same, should be true for all the prefixes. Check prime for this. Let's implement check prime. Boolean check prime takes in const string of reference, let's say number, convert it to n as string to integer. This is storable in a string, in a 32-bit integer. Yeah, so if n is less than equals to 5, it is prime only if it is 2 or 3 or 5. Let's start with the divisors. D is to D star D is less than equals to n D plus plus. If n mod D is 0, return false, otherwise return true. Okay, let's try this solution. Okay, so they are expecting the prefix to be not in the reverse order of looking at it. So what I need to do is, we don't need to reverse this, but we need to check whether to take the elements from the right or left. I think this is still incorrect. Let's try this naively. Or do we want to do this properly? What are we missing? So if you are in the second repetition, I can, so I was considering 32. So if I just reverse it, I'll get the actual. Let me bring this back. Repetition is 1. Let's do this. Okay. I hope this is enough. Cool. Let's go the next problem. You're given a positive integer k, find the smallest integer n divisible by k, and the smallest integer n divisible by k such that consists only of digit 1 in its decimal representation. Return an integer denoting the number of digits in the decimal representation of n. If it does not exist, return -1. So there is some peculiarity about this sequence 1111. It's represented like 1 plus 10 plus 100 plus 1000 plus and so on. And we want this number to be, when the smallest integer n, divisible by k. So this number should be mod k0. So we can find that out. This is a GP with first element as 1 and common ratio is 10. Let's say this is an GP of length t, or let's say L. What was the formula for, this is the GP, sum of GP formula. Sum of the first n terms of geometric progression with first term a and common ratio r is given by a times 1 minus r r is to n. Okay, it is 1 minus r raised to n divided by 1 minus r. So if you just flip the signs on numerator and denominator, it's 10 raised to L minus 1 by 9. Let's take some example. Let's say L was 2. Then this is like 100 minus 1, 99 by 9, which is 11. Correct. So we want to find smallest, right? So minimum L for which 10 raised to L minus 1 by 9. This is divisible by k. Let me write out an equation for this. 10 raised to L minus 1 by 9 mod k is 0. So 10 raised to L minus 1 by 9 is some constant time k. 9 times some constant time k. But what are we finding? We are finding n, which is L. Correct. So let me use a better terminology for this. 10 raised to n minus 1 is, since we want the smallest one, there is no, this c should be 1, I think. Not quite sure. Should be 9k. And we want to find n in this equation. K is known, c is not known, but we can 10 raised to n is 9k. The k dash. K dash is multiple of k plus 1. So n is simply log base 10 9k dash plus 1. If this is an integer, that is the answer. Otherwise, it is minus 1. What is the value of k? About 10 raised to 5. So we can brute force this, right? 10 raised to n is 9k plus 1. K is only 10 raised to 5. And 10 raised to has a form of like 10, 100, 1000. But we want to do this for all the multiples because this is k dash. 9k dash plus 1. Let's check this problem meanwhile. You're given an integer array nums. A subarray of nums is called centered if the sum of its elements is equal to the least one element is equal to at least one element within the same subarray. Number of centered subarrays. Sum of its element is equal to at least one element. Why is it like such a small constraint? Subarray of nums is called centered if the sum of its elements is equal to at least one element within that same subarray. And simple brute force, right? Subarray has someone which is also present. I mean, I can solve this, but let's not waste time writing two for loops. Yeah, let's move on to this one interesting problem. 10 raised to n. And the smallest integer n divisible by k. N divisible by k is 0. That consists only of digit 1 in its decimal representation. This has only 1, so it has a form of 1 plus 10 plus 100, so on. And this value comes out to be 10 raised to L. No, n is this. Smallest integer n, k minus 1 by 10 minus 1. So this is a GP with first term 1, common ratio 10, and we want this value to be divisible by k. 10 raised to n minus 1 is 9 k dash. Yeah, I think we arrived at this correctly before. What else is remaining now? 10 raised to n is 9k dash plus 1. Multiples of k. How can I even find out whether the solution exists to this or not? If it exists, then I can simply say that. No, I can't even say that because there are two unknowns in this. 9c k plus 1. C is unknown and n is also unknown. They're expecting the answer to be 32-bit integer, but I don't think that's necessarily true. There should be some proof related to this. 10 raised to n. Any multiple of k times 9 plus 1 should be. How can we verify that? Positive integer k, smallest integer n divisible by k that consists of only the digit 1 in its decimal representation. So it was minus 1 for k equals to 2. K equals to 2. 10 raised to n is 9 times 2 times c plus 1. K equals to 3. 9 times 3 plus 1 is 28, so that's not possible. The answer is 3. K equals to 3, answer is 3. So this was like 100, no, 1000, 9 kc plus 1. So 999 by 9 is C times 3. So C was, how much is this? 30, 21, no, 11. 21 is 7. Correct, right? 37 into 3. 21. 37 into 3, 21. Yeah. 37 was the multiple. No, I don't think we can simply brute force this then. Raised to n minus 1 by is ck. Wait, so we were at, maybe I have just over solved this problem. 9 is ck. K is known, C is not known. So we just need to check whether C is integer. We want to check for some n. This equation, this has a form of 9, right? So for n equals to 1, numerator is 9. For n equals to 2, numerator is 99. N equals to 3, it is 999. So numerator is 999, so on. Denominator is 9 times k. But we also need to find out what is the value of n for it. One thing that I can do is, once as I'm constructing this number, I can just compute the prefixes mod k. But I'm not quite sure where should we stop. And I can try brute forcing it. It can even pass or not, maybe. So for int n is 0, n can't be 0, right? Yeah. So in 1. So initially we have prefix as 0. Mod is also 0. Let's run this all the way up to 10 raised to 5. If we find it, we return, otherwise we return -1. Prefix, we don't even need to do prefix, just do mod equals to mod times 10 plus 1 mod k. If mod is 0, return n. It looks like it passed, but I'm not quite sure if it will pass for the rest of the cases. Okay, looks like it does pass. I'm not quite sure if why this limit is taken, but yeah, it was just a guess. I was going in the wrong direction of thinking, doing everything, but yeah, I think this should be it. I've solved quite a lot of problems and a lot of time. Yeah, see you.